Hello and welcome to a webinar discussion that we're going to have today with a couple of folks from the Tenaska Trailblazer Energy Center project in the United States. We're going to be talking about a couple of technical reports that Tenaska has provided to the Global Carbon Capture and Storage Institute. And I'd just like to introduce our two presenters today. We've got Mr. John Uphoff and Mr. Justin Vala from Tenaska, and they're going to be talking us through a couple of reports on the carbon capture plant layout, the steam turbine sizing, and also the air cooling work that they've done on their project. So without any further ado, I'll hand over to John and Justin, and they'll talk us through some of the findings that they've done with their studies. Over to you, gents.
Well, thanks, Crispin. Just real briefly, some quick introductions. I think it might be beneficial to just introduce quickly Tenaska. Tenaska is a private diversified energy company based in Omaha, Nebraska, and since its founding in 1987 has developed, built, owned, and operated 15 power plants, totaling about 9,000 megawatts of power generation. And the company is developing the Trailblazer Energy Center, which is the topic of this webinar. And we're going to talk more about what the project is in just a minute, but at a very high level, it's a supercritical pulverized coal-fueled power plant designed with 85 to 90% carbon dioxide or CO2 capture. From the development team, there's been primarily two engineers leading the effort. First is John Uphoff. John, you want to give your background very briefly?
Sure. I'm the project director for the Trailblazer project, and I've got previous experience with Mid-American Energy Company for 13 years in their coal-fired facilities. And I've also been with Tenaska for 11 years, since 1999. I've got a Bachelor of Science degree in Mechanical Engineering and a registered professional engineer in the state of Iowa.
And then on the other side, helping John, I'm Justin Vala, and I'm the manager of process engineering for Tenaska. For Trailblazer, like with some of the other work I do for Tenaska, I've been involved in technology evaluation and design engineering activities. Previous to Tenaska, I worked for ExxonMobil Chemical in technology and operations, and I have a Bachelor of Science in Chemical Engineering from the University of Nebraska-Lincoln. We'll move on. John, do you mind giving a brief overview of the project in a little more detail?
Sure. The Tenaska Trailblazer Energy Center is basically a 600 megawatt net pulverized coal plant. It's designed to capture 85 to 90% of the CO2 in a post-combustion capture process. The project is designed to use the CO2 to be sold for use in enhanced oil recovery. The amount of CO2 we expect to produce in a year is 5.75 million tons. And with that injection of CO2 into the ground, we expect that will produce 11.5 million barrels of incremental oil production per year in the area of the Permian Basin. Total capital project cost is somewhere between $3.5 and $4 billion. And the project site is in West Texas near Sweetwater. It's basically located between the towns of Sweetwater, Texas and Abilene, Texas.
And before we get into the reports here, just this slide summarizes at a very high level some of the key development milestones. The project's been under development by Tenaska for nearly 4 years. Let me highlight a few of the line items on this slide. Tenaska announced the project originally back in February of 2008. It's important that we mention that the project company is co-owned by both Tenaska and Arch Coal, who is the fuel supplier to the project. Also, Fluor has been selected as both the EPC contractor and the CO2 capture process technology provider. And we made those selections through separate competitive processes. And subsequently, Tenaska and Fluor have conducted a FEED study on the CO2 capture portion of the project with the support of the Global Carbon Capture and Storage Institute. In December of 2010, about a year ago, the project received its air permit. And then most recently, the project has signed a water supply agreement with the city of Stanford, Texas, which is relatively close to the project site. And again, highlighting something I said on the last slide, a key and mutually beneficial aspect of the project development has been our relationship with the Global Carbon Capture and Storage Institute. And as a result of our relationship, Tenaska has authored today 10 knowledge sharing reports on a variety of subjects. Those subject areas are listed here and include public engagement, infrastructure, technical reports, markets related, and financing. And I've highlighted over here 3 technical subjects which were mentioned initially that we're going to talk about in more depth on this webinar. And those are a layout optimization study regarding the CO2 capture plant, a study in which we evaluated steam turbine configuration and sizing for the power plant as it relates to the carbon capture unit. And lastly, we'll talk about a study in which we evaluated cooling alternatives for the project. So the first of these, again, is a report which summarizes an effort by Tenaska and Fluor to optimize the CO2 capture unit layout. And this is a graphic of that report and one of the key pages that's within the report. And summarizing that report and its contents at a high level, prior to when we completed the CO2 capture feed study, Fluor proposed and conducted an optimization study of the carbon capture plant preliminary layout. And we looked at 2 options. One kind of resembles a right angle, which was the base case, and the alternative was one in which the flue gas flow path traveled in more of a straight line, and we call that the inline arrangement. And looking at these 2 options, we considered a number of criteria in the evaluation. And some of those criteria included things like capital cost, equipment spacing requirements, obviously constructability, operating costs, and orientation of the air coolers. This project is air-cooled, which we'll talk about a little more in a minute. And the key result, we found that the inline configuration provided nominally $10 million or so of capital cost savings. And those 2 arrangements which we spoke about are depicted on this slide. On the left is the right angle arrangement, and on the right is the inline arrangement. And the black arrows depict the flue gas flow path for both of those 2 options.
Justin, it's Crispin here. Just a quick question on that. You note that there was obviously some synergies and some savings on the ductwork, which reduced the capital cost by about $10 million. Do you think that there's potential savings for other CCS projects when they look at some of these synergies overall? Do you think this is transferable, or is it just in particular for your project?
Yeah, I think so. I think that, broadly speaking, here, the main lesson for us, and then for others, is that really a compact plot plan, which brings the CO2 capture plant really as close as possible to the flue gas source and to the stack where it will be emitted, really represents the lowest cost configuration. We found that minimized the quantities of things like large flue gas ductwork and alloy piping and structural steel. So I think that general conclusion is probably transferable to others.
Sure. So that's really one of the main lessons from this report, really, is to try and co-locate it as closely as possible.
Yeah, and I think what we saw in the range of 1 to 2%, again, the $10 million is in the range of 1 to 2%.
Yeah.
Savings.
Not insignificant. Yeah.
Yeah, absolutely.
Okay.
So continue. John, will you speak about the steam turbine configuration report?
Sure. This first slide is kind of the cover page for the report that was issued, along with one of the intermediate sheets within that report. Looking to the next slide here, the steam turbine configuration and sizing report. I'm just going to go through the bullet points here. It was really a leading post-combustion CO2 capture technology that requires a large volume of steam. So the required steam would be extracted from the steam cycle, and with us being a greenfield project rather than a retrofit project, Tenaska and Fluor were able to specify the optimal steam turbine design for the project. The report covers studies conducted by Fluor and Tenaska with the support of major steam suppliers, steam turbine suppliers and manufacturers. And we evaluated the steam cycle extraction pressure and location, which was essentially the IP, intermediate pressure to the low pressure crossover portion of the turbine. Secondly, we were accommodating an air-cooled condenser for the site ambient conditions. And lastly, we decided whether to design the LP section for the full flow steam flow, which we call the big turbine case, or the reduced LP steam flow with the carbon capture plant is online, which we call the small turbine case. This next slide is just a depiction of the simplified steam cycle diagram with the highlighted section of steam supply going to the carbon capture plant.
John Crispin again here. I just wanted to ask just the conclusion that was reached from this study. You previous slide talked about a big versus small turbine. Just remind our listeners, can you, what decision was made by Tenaska and the sort of the basis for that?
Well, first off, I think that the main thing we learned from that report is that we confirmed that the steam requirements of the CO2 capture plant could be met with the currently available technology. So when we did go out to the existing vendors, we didn't ask for them to design a new turbine specifically for the Trailblazer site. We asked them to use existing turbine technology, and I think that confirmation was very important. And as far as the big turbine option provides a maximum operational flexibility in that it provides additional power generating capability. And that capability more than compensates for the small difference in the capital costs. So I think that's one of the major things we learned, and one of the bigger benefits of selecting the big turbine option.
Yeah, so the big turbine really fits the bill in the Texas electricity market that you're in, but also being able to supply CO2 to the Permian Basin.
Correct.
Yeah. Thanks.
And the third study that we'll summarize is an effort to evaluate cooling alternatives for the project. The project is located in West Texas, and with the climate there, which is fairly arid, that limits the amount of water that's available. Actually, that's been a difficulty for the project development in some regard. This study covers the three options that we considered, which were air cooling, conventional wet cooling, as with a cooling tower, and partial wet cooling, or kind of a hybrid of the two. And the result of the study is that we selected air cooling for both the power and the CO2 capture portions of the project. And other than that, that's pretty much the summary of those three. From the global standpoint, do you guys have any more questions?
Yeah, I just had a couple of questions on the cooling report. Could you just explain the methodology of evaluating the different cooling options that you had?
Yeah, we did something that's fairly common in engineering economic evaluations. We just used a present value analysis to compare these options. And that analysis, of course, then took into account the relative capital costs, which were estimated by Fluor, and then as well as discounted cash flows for the relative operating costs, the differences in performance and CO2 production rates, and also the water consumption. And all those economic assumptions that underpin that analysis are written out in the report.
Yeah, it's an interesting point, Justin, because I just wanted to ask you as well about how do you weigh the various technical issues against some of the economic issues, but also importantly the public acceptance issues, because as you mentioned in other reports, water is a fairly emotional issue out there in a semi-arid area. So how do you put relative weightings on the different factors that go into this decision?
Yeah, that's an interesting question. Being an engineer, I always prefer a real clean, calculated answer with economics and technical criteria. But in this case, I think for Trailblazer, in reality, the most important criteria is just the ability to secure adequate water supply. And that's kind of somewhat tied to the public acceptance issue. And I can say that in part because, really the study results were positive for us as far as the feasibility and apparent cost effectiveness of air cooling. And so in the end, the economic and technical solution matched up with what is really required to develop the project.
Sure. Can you tell us any more about the water issue and how Tenaska is dealing with that more broadly, given its importance in that region?
Yeah, we're talking about first and foremost minimizing water consumption, and obviously utilizing air cooling. And I think we said this on the slide that we're able to reduce our water demand by something like 90% or so. And there's other things that we're doing to minimize water. The remaining water-based cooling systems, we have very high cycles of concentration in the design, as well as we've incorporated a zero liquid discharge process, which in the end vaporizes the water such that it can be condensed and recycled back. And another interesting aspect of utilizing carbon capture is that the cooling of the flue gas results in some condensation of some water that can be captured and recycled. And then, lastly, we've really focused on sourcing, municipal wastewater that tends to be more acceptable to the public as far as water utilization in the area. And recently we were successful in securing water supply contract from the city of Stamford.
Mm-hmm. Okay, thanks very much for those answers. I just wanted to reiterate to listeners that all of these reports are available on the Global Institute's website. If you would like to find out more about the Tenaska Trailblazer project, you can have a look at this website that we've got up here. There's some interesting diagrams and animation on how the project will work and how CCS works. But I would like to take the time to say thanks very much to John Uphoff and Justin Vala for their time today to walk us through those reports, and you'll see the Global Institute's website. So, gents, thanks very much for your time today.
You're welcome. Thank you.
Thank you.